Hello, my name is Adam Pease, and I'd like to talk today about my summary of what is artificial intelligence. Very broadly, AI is the science of teaching computers or programming computers to do some of the same things cognitively that people do, or to do tasks that could be done in other ways, possibly, but doing them in a way that mimics at least what we know about how people solve problems. A central problem, however, is we don't actually understand how people do things. We have some ideas, we have some models, we have a lot of science that's zeroing in on things, but at a very basic level, we don't really understand how people do many of the mental processes that they do. And as a corollary to this, and something that AI has suffered from greatly, is that once we know how to do something, it stops being mysterious. It stops being artificial intelligence and instead is generally called, a sort of a known algorithm or a known approach to things, as opposed to this magical thing we call AI. Early AI was quite different than it is now. It involved what we might broadly call symbol manipulation. Things like search, a lot of work in programming languages to come up with new ways beyond the original languages like assembly language and COBOL and Fortran that allowed us to deal more easily with symbols instead of just numbers. And all of this was also centered around knowledge representation. How do we record what we know about the world and record it in a way that makes it suitable for the machine to do some processing with that knowledge? Along with that, we had expert systems, very broadly the techniques of using rules and combining those rules dynamically to reach a conclusion to a question that might be asked. This is an application or a set of applications that was actually very commercially successful for quite a while, around the 80s. There was a big boom in AI at the time. And rule-based systems, things like business rules, are still used extensively in a lot of different contexts, but they're a prime example of how when something became well-known and common and easy to do, that it ceased to be described as artificial intelligence. There's lots of work in planning and robotics, much of which now has really been superseded by the numerical techniques. Reasoning and theorem proving continues as a very active research area. Proving mathematical theorems, there's been some success with that. Case-based reasoning, analogical reasoning was a very rich area of exploration for a while, now is not receiving all that much attention. Natural language parsing, although it has its origins in early AI, now is done primarily through machine learning techniques. But all of the ways in which we describe language, all the annotations we put on language, the fact that we do mark parts of speech and we have standards for things of how they do that, all of that grew out of this work in very early AI. Numerical algorithms certainly also have a long history, things like perceptrons, or even simpler, sort of what you might call heuristic, but numeric techniques for information retrieval have a very long history. So here's just a summary of the various applications or sub-areas that I've just talked about. In particular, things for like information retrieval, TF-IDF algorithm, BM25, reasoning and theorem proving. There was certainly continued to be a lot of applications in VLSI design. But these aren't the hot things right now. The hot things I will talk about in a moment, but as a way to put them in context, we could look at this in terms of cognitive science. How do we describe what people do in their heads? And broadly, you could say there are perception activities, sensory activities, things we do with our five senses that are very fast. They're pattern matching kinds of activities, and they're also approximate. So we can recognize faces from any angles, even if it's obscured, even if the face is dark. It happens instantaneously, and it's not a conscious thing. It's something that we do in visual perception, or we could do the same thing in recognizing a voice or hearing words through audio perception. Cognition, however, has different characteristics. It's more deliberate. It's about reasoning. It's often, although not always, precise. We come to a yes or no kind of conclusion. It's also amenable to book learning. You can learn rules of thumb, you can learn facts, you can learn how to accomplish things, you can learn procedures. And this is done not necessarily through millions of repetitions, like seeing a face a lot of times, but it can be done instantaneously by reading a fact in a book and assimilating it. Modern AI has had tremendous success, especially tremendous commercial success, in doing the sort of perceptual activities. There have been a lot of different techniques that even just a few years ago used to be very popular, support vector machines, Bayesian networks, things like conditional random fields. A lot of that has now been supplanted by deep neural networks, especially deep neural networks on specialized hardware like GPUs. Things that were completely computationally impossible years ago that might have at the time been considered just brute force now are eminently possible and incredibly powerful. So it's not only the techniques have improved, but the computing power and the computing architectures have improved, and also the access to enough data to make this sort of large-scale training feasible has now also changed quite dramatically from even 10 years ago, maybe even 5 years ago. So applications we're seeing in modern artificial intelligence are things like self-driving cars, face recognition, voice recognition, text-to-speech, some success in machine translation, a lot of work on what we might call closed worlds, things like various games, including playing video games, having a machine that can play video games better than any human video game player could ever do. Applications in credit approval, fraud detection for credit card companies, question answering chatbots, things like Amazon Echo, Google Home, Apple Siri. These are all big successes, big commercial successes. But what's next? My sense is that the next frontiers are going to be at the integration of perception and cognition. The hard problems about reasoning, about coming up with a line of deduction for a particular conclusion, especially about very complex things, these haven't gone away. Computers are very good at telling you, here's a match for what you're asking for, but they're not so good at combining information from multiple sources to come up with a new conclusion. If you imagine, if you want to reason about hypothetical things in the future that are very complex, say you want to reason about what's going to happen in politics around a certain issue, and you might have a human being that could answer that question and give you a line of reasoning. I think this is going to happen because A, B, and C. Machines are not so good at doing that sort of thing, and those are really valuable problems to be able to solve. I've come up with the term cognitive guardrails as being something that's important. We've seen this a lot in some recent events in self-driving cars. The tragic death of a pedestrian a while back. A machine doesn't know inherently the value of, say, human life, or to be able to reason that if I see a ball bouncing across the street that there might be a small child following it. It may have, if it's been trained on a very similar situation, know that it needs to brake, but if it hasn't been trained on this situation, coming up with the right reaction at the right time in the right way will be very challenging. And of course, it can also be challenging for people. There are accidents on the road all the time. But where I think we want the field to go is to be able to have these cognitive guardrails, these rules of thumb, this understanding of how the world works that can be presented to machines in text, in rules, to be taught very quickly in summary instead of by millions and millions of examples, that will help guide the machine to do the right thing in the real world with some common sense, as well as do the right complicated instantaneous reactions or pattern matches with things based on training from large data. So that's my perspective, and I hope you found this helpful.